All right, let's get right into it. Today, we're going under the hood of one of the most incredible breakthroughs in AI, models that can actually see and talk. We're going to break down the technical architecture that makes all of this possible, piece by piece.
Okay, so here's our game plan. First, we'll look at what these models can actually do. Then, we'll dive into the three core ingredients that make them tick. From there, we'll trace the whole evolution, compare the different architectures out there, and finally, take a little peek into what's next for multimodal AI. So first up, let's talk about the breakthrough itself. I mean, we are living through a truly remarkable moment where the line between an AI understanding language and understanding our visual world, well, that line is basically dissolving right before our eyes. And this all boils down to one fundamental question, right? How do these systems actually do it? How do they look at a complex scene, a picture, or even a video, and then describe it with the kind of nuance we'd expect from a person? And this isn't some theoretical, far-off future stuff. We're talking about real capabilities that are here right now. You've got GPT-4V, which can look at a screenshot of a website and just write the code for it. You've got Gemini, which can watch a video live and give you a running summary of what's happening. And Claude can take a technical diagram you drew on a whiteboard and explain its architecture back to you. This is the new reality. So how in the world did we get here? Well, this wasn't just a single invention. It was really the perfect storm, the convergence of three foundational technologies. Let's break down those building blocks.
This whole journey really rests on three key pillars. First, you have the original transformer architecture. Second, you have the incredible adaptation of that for images, which we call vision transformers. And third, you have the fusion of those two worlds into what we now know as vision language models, or VLMs.
Everything, and I mean everything, starts with the transformer. You can think of it as this universal engine for processing sequences. It was a complete game changer for language because it could handle words in a sentence, but its real magic is its flexibility. It doesn't care if it's text or musical notes. If it's a sequence, the transformer can probably handle it.
Now, here's where the big aha moment happened. The vision transformer, or VITE, took that same sequence processing power and pointed it at images. The key innovation, the real genius of it, was to stop seeing an image as just a grid of pixels. Instead, they broke it down into a series of smaller patches. And just like that, an image became a sequence. Just like a sentence is a sequence of words.
So, with those core ingredients in place, the stage was set for an absolute explosion of new architectures. Let's trace that evolutionary path and look at the key models that really paved the way to where we are today. This timeline really tells the story. You start with models like Clip, which absolutely mastered aligning images with their text captions. Then, along comes Flamingo, which pioneered this idea of injecting visual info into a language model using something called cross-attention. It's like letting the text model peek at the most important parts of an image. After that, LLaVA came up with a really clever shortcut. Just translate the image patches directly into language tokens. And all of this work laid the foundation for the massive, built from the ground up models like GPT-4V and Gemini. To really get this evolution, it helps to compare the two early schools of thought. On one side, you have Clip's approach, which is all about alignment. Think of it as a super-powered matching engine. It's fantastic at finding the right caption for an image, but it can't create anything new. On the other side, you have Flamingo's approach, which is about injection. It built a kind of bridge to feed visual features into a language model, which then allowed it to generate brand new original descriptions of what it was seeing.
And that brings us to LLaVA's brilliant contribution. See, instead of building a whole complicated bridge between the vision and language parts, LLaVA's architecture it translates. It translates the image patches into the language the LLM already speaks. It turns visual data into word-like tokens. It's a hugely efficient shortcut to get a powerful language model to see.
So let's get practical. For anyone out there actually building with these systems, the most crucial thing to understand is that each of these designs comes with a very specific set of engineering trade-offs. There's really no one-size-fits-all solution here.
This table really lays it all out for you. A Clip-style architecture? That's your go-to for classification or search, but remember, it can't generate new content. A Flamingo-style model? That gives you that awesome generative flexibility, but you're taking on more architectural complexity. The LLaVA approach is super efficient since it just piggybacks on existing LLMs, but your results totally depend on how good that vision-to-token translation is. And finally, you can train a monster model from scratch like GPT-4V.
It's potentially the most powerful option, but it comes with an absolutely astronomical training cost.
So here's the bottom line. The architectural choice you make is the decision. It directly defines what your system can and can't do. For any engineer working in this space, understanding that relationship, well, that's everything.
All right, let's wrap this up and look to the horizon. We've seen how these models have evolved, and the direction we're headed is crystal clear. We are going deeper and deeper into a truly multimodal era of AI.
So here are the key things to take with you for your next project. 1. Architecture defines capability, period. 2. You are always making a trade-off between efficiency, flexibility, and just raw power. 3. Mastering those trade-offs is what separates a successful project from a frustrating one. And finally, get ready. We are just at the very beginning of what's possible when models are multimodal from the ground up. Which leaves us with one last, really provocative thought. We just watched AI learn to connect sight with language. So as we keep fusing more senses, sound, touch, maybe others we haven't even thought of, what completely new capabilities are going to emerge that right now we can't even begin to imagine?
If you found this helpful, hit subscribe and the bell so you never miss a video.